So my co-author, Andrej Zupanc, is sitting over there at the back. Now, the paper is about diagnosing Parkinson's disease from person's voice. Now, the basic idea here is that we would like to detect signs of Parkinson's disease by the analysis of the person's voice. Early work done by that we are aware of was done by Max Little and Anastasios Tsanas in about 2010, when they were interested in the monitoring of the progress of disease in Parkinson's patients. So that, I suppose, was quite successful, and there's a fantastic talk, TED talk by Max Little on what they did in that work. But all TED talks look fantastic, so so we don't know exactly whether that really was so successful. Basically, that made us think about how this same approach could be used to the learning to diagnose, the learning of diagnostic models, so not monitoring the progress of disease, but to diagnose patients with machine learning from the recordings of their the voices of patients and healthy persons. The practical motivation is this would enable us to build a simple tool for everybody to help in early detection of Parkinson's disease. It is a sort of similar, in the similar spirit as a mobile application that we did some time ago, 2014, which is called Parkinson Check, and that is based on the use of spiralography. Now, in our work, we actually used data that is available on the internet, publicly available or under very easy to satisfy conditions. So these were the used databases. Two of them were contributed by Tsanas and Little. Okay, there are some limitations in that work. They only had recordings of 42 patients, altogether about 5,800 recordings collected through a period of 6 months. And in another database, they had they had 23 patients and also some healthy persons. In all these databases, the recordings were not actually present. The original sound recordings were not available, but instead the recordings were represented by 26 acoustic attributes, or in this case 23 attributes. So what we could use for machine learning was these 23 or 26 attributes. There's another database, Bionetworks database, with about 65,000 sound recordings. So that is a much better source. Now, in all the cases, the recorded sound was about 10 seconds of the sound A. So, I have a few recordings, but since we are here, since we are short of time, I'm just going on through the presentation. So here are some details of the Sage Bionetworks database, the largest one. A number of people that we could use for learning was actually close to 3,000. And for typically the same person had several recordings of their voice, and typically we only used, actually we decided to use only the first recording of their voice because there was a speculation that there might be an effect of a person's adaptation to the system. We're not sure whether that would actually happen. Now, there's a note to be made regarding the quality of the data. The correctness of the answers, I mean, this database was collected through a portal, and the people were asked to record their sound and also to fill in a questionnaire. So the correctness of the person's answers was not verified by any medical expert. And the answers also included whether they were suffering from Parkinson or not. Okay, now the first two databases, 1 and 2, by Little and Tsanas, we had quite a lot of problems with them, and the basic problem was that the databases were very much imbalanced with respect to the two classes, healthy or a patient. And the healthy recordings were much underrepresented. So this imbalance causes problems to machine learning. Of course, the results that we obtained from of learning was that the resulting accuracy was very high, okay, over 99%, which is immediately suspicious, but of course, with such an imbalanced data set, what else can you expect? We did use some methods that try to compensate for this imbalance, like under or oversampling. These are the names of the methods, but I mean, even that, I think, cannot really cope with that. So in the end, we don't believe that these results are realistic, and therefore in the sequel we only used Sage Bionetworks database, so the largest one. The techniques and tools that we used were scikit-learn, collection of machine learning tools, Keras, an implementation of deep neural networks, and then two program libraries for voice analysis. These two libraries allow to compute attributes of the recording from the recording itself. So in the case of this library, we can compute 23 attributes, so the same attributes that Little and Tsanas used. And there is another library available, OpenSmile, which computes a rather larger number of attributes, over 6,000. Now, in all cases, we estimated the classification accuracy with tenfold cross-validation. Now, here are the results. With 23 attributes, so learning from the smaller set of attributes produced by voice analysis toolbox, the most successful machine learning method was support vector machines, which produced the accuracy 67%. So that is the accuracy in predicting the binary decision, making the binary decision whether Parkinson is present or not. Now, with this larger, with attributes from OpenSmile, so the larger set of attributes, over 6,000 attributes, support vector machines, okay, obtained rather significantly higher accuracy. But in that case, working with such a large number of attributes, we need something more appropriate for this amount of attributes, and it turned out that gradient boosting classifier, which is an ensemble classifier based on decision trees, was was even more successful. So that obtained the accuracy over 80%. So we believe that 80% is about the state of the art that we can achieve from this data. However, there is then another question which was actually pointed out to us by Professor Petrošek, who I was hoping he would be here today, but probably he could not. Yeah, he could not make it here. But anyway, we did discuss that with him a few weeks ago. And the problem is that there is an imbalance in the Sage Bionetworks database in that the majority of healthy people are young, and the majority of unhealthy people are old. I think there is a saying that Parkinson's disease is the disease of the old people. And I think that's the thing. Okay, so the question is the system actually detecting the voice signs of Parkinson's disease or simply the signs of age? And the distribution, the particular distributions, I had to translate my presentation during the session today because I assumed that it was going to be, the conference was going to be in Slovene. So this remained from my Slovenian slides. So that is the distribution of the people according to the age. So here we have age, and here we have the frequency of people with that age. And that is, okay, that is the distribution of all the persons recorded in the database. So remember this for a moment. Now, this is the distribution of healthy people. Okay, so this is even more to the left. So the dominant class is well, basically these people are young, and this is the distribution of, in the same database, of people suffering from the disease, and of course this is very much more to the right. So these are much older, and that puts a question mark what is to be done next to take into account the effect of a distribution of age. Now, a more interesting development, more recent one, that was done by Andrei maybe a week or so ago, was learning with neural networks. Now, with neural networks, we could use deep learning from the actual sound recordings. So not to go through these attributes that are computed by sound analysis, but directly put this sound data into the machine learning tool. And this would, the important thing is, this would, at least in principle, enable discovery of important new attributes. So attributes of voice attributes that maybe even medical doctors have not thought of, they could be discovered automatically in this way. Now here are some preliminary results. With a 5-layer network, obtained accuracy 68%, with a 6-layer network 63%, which is still lower than gradient boosting results. But here are then several questions. Is this appropriate, 5 or 6 layers? It may be that 5 layers might already be too many, because to make a neural network work, you need to set many get many parameters right. So that I hope we will be able to do in the future better. Okay. Now, Andrei also developed a mobile application on smartphone for recording and diagnosing person's voice with diagnostic model induced from Little and Tsanas data. So this is something which works, but that is, of course, as we know, problematic because the source of data was too imbalanced. My question would be, would it be practical or practical relevance to adapt this application to use diagnostic model developed from the Sage Bionetwork networks data. And I will thank you for your attention.